Hi, now let's move on to hyperparameters. One of the most important hyperparameters is learning rate. The right learning rate is critical for fast convergence. If it's too strong, then our gradients might actually overshoot and bounce, so we might in fact be close to our optimal solution. However, because of a very strong learning rate, we might get larger and larger errors. If the learning rate is too weak, on the other hand, we have very small gradient steps, which means very slow training, and also we might get the false impression that we get no improvement no more, so we should stop the training. Importantly, quite often a different learning rate per weight is advantageous, as some weights might be near convergence while others are not. For this, using adaptive optimizers like RMSprop or ADAM is quite beneficial. In theory, we have to make sure that whatever learning rate we pick, learning rate schedule we pick, the following two conditions are satisfied. For one, the sum of learning rates over time goes to infinity, while the sum of the squared learning rates is smaller than infinity, does not go to infinity. Intuitively, the first term ensures that we're going to search enough, like we're going to explore enough, while the second term ensures that we're going to converge to a solution. As per the learning rate schedules, there are different options. We can have a constant learning rate throughout the whole training. We can have step decay, where we reduce the learning rate every t epochs. We can have inverse decay or exponential decay of our learning rate. In general, step decay is actually a good choice. It's simple, it works well, so quite often we use that one. And in practice, we try several log-spaced values to begin with on a smaller set, and then we narrow it down from there based on what gives us the better validation error. We can decrease the learning rate every t epochs, as we saw in the step decay, and we also need to understand that this, of course, depends on our data. So try it on your validation set and see what works better. The dropout rate is another hyperparameter. Generally, we have to start with a relatively small rate, in the range of 20 to 50%. If it is too high, then our model actually might underfit. We might have a weak model to begin with. With dropout, a good thing is that we can actually have even larger networks, so that's a good thing. Regarding the batch size, if possible, we should try to have at least a batch size, a mini batch size of 32. In general, our mini batches should, we should have them as big as our GPU memory fits. The number of layers in neurons is always a big question. So there are no theoretical suggestions, I believe, but for a new problem, my recommendation would be to generally start from moderate sizes. Don't start from a single layer neural network, but also don't go to 50 layers. Start with 3 to 5 layers with a few dozen neurons at most. The thing is that if you start with a very complex model and it doesn't work, it's very hard, or it's actually much harder to debug it. You don't know if it doesn't work because the model choices are wrong, as in like the specific model type of architecture, or is it that the model just overfits? What exactly is the problem? Whereas if you start from a small model and then you get reasonable performance, you can always increase the complexity and then see where it stops improving. For a known problem, for instance, image classification, you can reuse the hyperparameters that are suggested by the whatever model of choice you're starting from, if you're starting from an existing model. Overall, when babysitting deep neural networks, some things to keep in mind is that you should always check your gradients if these are not computed automatically by your PyTorch or TensorFlow and whatever. In the first round, you should check that your predictions are random, that you get a loss that corresponds to random guesses. You should turn on and off your regularization. With the regularization, you should get a bit higher error because you're adding one extra term, positive term. Always keep a separate validation set such that you can do early stopping, and also you can select hyperparameters. Pre-process your data such that we've got centered activations. Initialize your weights based on your activation function, so be careful of the initialization. Use regularization techniques wherever possible. Batch normalization in practice is very crucial, especially with very deep networks and with complicated architectures. And last, I would recommend that you use residual connections whenever possible. We haven't discussed yet what residual connections are, but keep that in mind. They actually make a very big difference. Quite often, residual connections make a model work, whereas before it simply didn't. So here I have added some extra reading material. And this is it for today. We saw advanced optimizers, initialization, normalization, regularization, and hyperparameter tuning techniques. So basically, most of the tools that you will need to optimize your neural networks. And I hope that now you can actually train your first neural networks successfully. Thank you very much. Bye.